Ever wondered how your digital devices work so efficiently? It's a fascinating world inside those sleek casings, where a symphony of electronic signals translates into the functions and features we all rely on daily. This realm is governed by the principles of digital electronics, with key parameters defining how our devices operate. In this journey into the digital heart of your devices, we'll explore parameters such as bit rate, clock frequency, propagation delay, and rise and fall time. We'll dive into the concepts of setup and hold time and look at the importance of power consumption. We'll also delve into design elements like fan out and fan in, noise margin, logical effort, and power delay product. We'll even touch upon the significance of IC size and density, and the different types of power consumption. Each of these parameters plays a crucial role in the performance of our digital systems. Stay tuned to learn how these parameters make your digital device tick. Think about how fast your digital device processes data. This speed is largely determined by two key parameters, bit rate and clock frequency. The bit rate refers to the rate at which bits, the basic units of information in computing, are transmitted or processed. It's like the speed at which a digital system talks. This is measured in units like bits per second, kilobits per second, or even megabits per second. So when you're streaming your favorite show and it's coming through without any annoying buffering, you have a high bit rate to thank for that smooth experience. But there's another player in the game, the clock frequency. This is the heartbeat of a digital system, the rate at which the clock signal oscillates. Think of it like the conductor in an orchestra, dictating the tempo for all the components to follow. It's measured in units like hertz, megahertz, or even gigahertz. The higher the frequency, the faster the operations are synchronized and executed. Together, these two parameters play a pivotal role in determining the speed at which your device operates. A high bit rate means more data can be processed in a given time, leading to faster data transfer or processing speeds. Similarly, a high clock frequency ensures faster synchronization and execution of operations, thereby increasing the overall speed of the system. But just like in life, balance is key. Higher bit rates and clock frequencies can generate more heat and consume more power. So engineers have to find the sweet spot, optimizing both to ensure efficient and effective operation of digital systems. So the next time you download a file or play a video game, remember the bitrate and clock frequency are at work, making sure your digital experience is as smooth and fast as possible. Ever noticed how instantly your device reacts to your commands? That's all thanks to two key parameters in the digital world: propagation delay and rise-fall time. Let's start with propagation delay. It's the time taken for a signal to travel from the input to the output of a digital circuit. Think of it as an electronic echo, where the delay is the time between when you shout and when you hear your voice bouncing back. It's usually measured in seconds or nanoseconds, which speaks to the lightning-fast speed of modern devices. The shorter the propagation delay, the quicker a device can process and respond to a command. Now, on to rise and fall time. These terms refer to the time it takes for a signal to transition from a low to high state, known as the rise time, and from a high to low state, which is the fall time. Imagine a light switch. The rise time is the moment you flip the switch to when the light fully illuminates, and the fall time is from when you flip it off to when the room is completely dark again. These transitions are measured in seconds or nanoseconds, just like propagation delay. Rise and fall time are critical to maintaining signal integrity. A slow rise or fall time can lead to signal distortion, affecting the overall performance of the circuit. So why do these parameters matter? They directly impact the speed and performance of your digital devices. A device with a small propagation delay and quick rise and fall times can process inputs and outputs faster, making it more responsive to the user. On the flip side, a device with a long propagation delay and slow rise and fall times might seem sluggish or unresponsive. It's like having a conversation with someone on the moon. The delay can make communication frustrating and inefficient. In a nutshell, propagation delay and rise-fall time are the unsung heroes of our digital age. They work behind the scenes to ensure that our devices are responsive and efficient, making our digital experiences seamless and enjoyable. These parameters ensure your device is responsive and efficient. Let's delve into the inner workings of your device. Our journey takes us next to the concepts of setup time and hold time. These are critical timing parameters in digital systems. Setup time is the minimum period that data input must be stable before the clock edge for the system to function reliably. Hold time, on the other hand, is the minimum duration that data input must remain stable after the clock edge. Both of these are typically measured in seconds or nanoseconds. Why are these parameters important, you ask? Well, they ensure proper timing relationships between signals. Having correct setup and hold times keeps our system operating smoothly and without errors. Imagine them as the conductors, orchestrating the symphony of data flow in our digital systems. Now let's switch gears and talk about power. Power consumption is the amount of electrical power that a digital circuit or system uses. It's typically measured in watts or milliwatts. Power consumption is crucial for several reasons. First, it plays a significant role in the energy efficiency of our devices. The lower the power consumption, the longer our device can run on a single charge. Second, it's crucial for thermal considerations. High power consumption can lead to excessive heat, which can damage the device or decrease its lifespan. So managing power consumption is a balancing act. We want our devices to perform well, but we also want them to stay cool and run for a long time. In essence, setup time, hold time, and power consumption are like the heart, lungs, and metabolism of our device. They keep everything running smoothly, ensuring that our devices can perform their tasks quickly and efficiently, without overheating or draining their batteries too quickly. These parameters keep your device functioning correctly and efficiently. Ever wondered about the design aspects of digital circuits? Well, let's dive right in and talk about fan-in and fan-out. Fan-in refers to the number of standard logic inputs connected to a gate or circuit. It's like the number of roads leading into a city. More roads mean more traffic can flow in, but it also increases complexity and can affect performance. Fan-out, on the other hand, is the maximum number of standard logic inputs that a digital output can drive. Think of it as the number of cities that can be reached from one city by road. It influences the design of digital circuits and ensures proper signal integrity. Now let's shift gears and talk about noise margin. It's the amount by which the signal can be reduced before it becomes unreliable. Imagine you're trying to listen to a radio station while driving through a tunnel. The noise margin is like the strength of the radio signal before it gets too weak to hear clearly due to the interference from the tunnel. It measures the robustness of a digital circuit to external noise. Lastly, we have logical effort, a measure of the effort required to drive a certain load in a digital circuit. It's like determining the effort you need to pedal a bicycle up a hill. The steeper the hill, or the larger the load, the more effort you need. Logical effort helps in optimizing the sizing of transistors in a logic gate for speed and power efficiency. So, in a nutshell, fan-in and fan-out deal with the inputs and outputs of a circuit. Noise margin tells us how much a signal can be reduced before it becomes unreliable, and logical effort measures the effort needed to drive a load in a circuit. These parameters ensure the robustness and efficiency of digital circuits. So, how does all this information help you understand your digital devices better? You may wonder. Well, by understanding these parameters, we can appreciate the intricacies of the digital world. We've talked about the bit rate and clock frequency, which dictate the speed and synchronization of our devices. We've delved into the propagation, delay, and rise and fall time, which impact the overall performance and signal integrity. We've also explored the setup and hold time, ensuring proper timing relationships between signals, and the power consumption, a key factor for energy efficiency. We've discussed fan-in and fan-out, which influence the complexity and performance of digital circuits. We've touched on the noise margin, measuring the robustness of a circuit against external noise, and logical effort, helping us optimize transistor sizing for speed and power efficiency. In essence, these parameters shape the performance, efficiency, and reliability of our digital devices. Next time you use your digital device, remember the intricate parameters that make it work so efficiently.